4 light-years away sits a star almost identical to our Sun. For decades, astronomers desperately wanted to know if planets orbited it. Every attempt failed. The star was too bright, its companion too close, its motion too fast across our sky. Then the James Webb Space Telescope pointed its golden mirrors toward Alpha Centauri and captured something that made scientists gasp. A faint dot of light appeared beside the star, then vanished. Follow-up observations found nothing. The planet, if it exists, had disappeared. What James Webb discovered in our closest stellar neighborhood defies everything we expected about finding worlds beyond our solar system. Now, get comfortable, and let's begin. Alpha Centauri is not just another star scattered across the night sky. It represents humanity's closest stellar neighbor, the first stop on any conceivable interstellar journey, the cosmic front porch of our solar system. For more than 70 years, astronomers have obsessed over a single, haunting question. Does it have planets? The answer seemed perpetually out of reach, not because technology didn't exist to find worlds orbiting other stars. Scientists have discovered nearly 6,000 exoplanets using methods refined over decades of innovation. Gravitational wobbles reveal massive planets tugging on their host stars. Periodic dimming exposes worlds crossing stellar faces during transit events. Direct imaging captures the faint glow of young, hot planets orbiting distant suns. The problem was Alpha Centauri itself. This star system breaks every rule astronomers developed for hunting planets around other stars. Its unique characteristics transform what should be the easiest target in the sky into perhaps the most challenging observation ever attempted. Alpha Centauri sits just 4.37 light-years from Earth. In cosmic terms, this qualifies as spitting distance. Light leaving the system tonight reaches your eyes in less than 4.5 years. A photon departing Alpha Centauri when you started high school arrives before you finish college. Compare this to typical exoplanet host stars which lie hundreds or thousands of light-years away. The nearest confirmed transiting exoplanets orbit stars dozens of times farther. Most directly imaged worlds circle stellar furnaces located hundreds of light-years distant. Alpha Centauri practically shares our cosmic backyard. This closeness should make planetary detection trivially easy. Nearby objects appear brighter and larger than distant ones. The same planet that vanishes into stellar glare at 100 light-years might shine clearly at 4. Proximity should provide overwhelming advantages for anyone targeting our nearest stellar neighbor. But with Alpha Centauri, proximity creates problems rather than solutions. The system shines with blinding intensity that overwhelms the sensitive instruments designed to detect faint planetary signals. Imagine trying to photograph a firefly hovering beside a searchlight. The searchlight's glare drowns everything in its vicinity. That's the challenge astronomers face every time they point a telescope at this system. Alpha Centauri A, the largest star in the triple system, ranks as the third brightest star visible from Earth's surface. Only Sirius and Canopus outshine this blazing stellar furnace. On clear nights in the southern hemisphere, it dominates the constellation Centaurus with a yellow-white brilliance that ancient navigators used to chart courses across unknown oceans. Its companion, Alpha Centauri B, orbits close enough to compound every problem the primary star creates. The two sun-like stars circle their common center of mass every 80 years, approaching within 11 astronomical units at closest passage and separating to 36 astronomical units at maximum distance. During observations, the companion floods detectors with contaminating light that obscures any faint planetary signal around the primary. No coronagraph in existence can simultaneously block two bright stars positioned at different locations on a detector. A distant third member called Proxima Centauri lurks roughly 13,000 astronomical units from the central binary pair. This dim red dwarf barely qualifies as a star, shining with less than 1% of solar luminosity. Scientists already confirmed that Proxima hosts at least 2 planets, with a possible third candidate still under investigation. But these worlds orbit a star so fundamentally different from our Sun that comparing them to Earth makes little scientific sense. Red dwarf planets face violent stellar flares that strip atmospheres within geological timescales. Tidal locking turns one hemisphere toward eternal day while the other endures endless frozen night. The real prize was always Alpha Centauri A and B, genuine solar twins radiating the same warmth and the same invitation as our own Sun. These 2 stars resemble our Sun in nearly every measurable characteristic. Their masses, radii, temperatures, and ages match solar values within close margins. Alpha Centauri A has existed for approximately 5 billion years, roughly the same age as our Sun. Any planets orbiting this mature star would have long since lost their formation heat. They would shine only through absorbed and remitted stellar radiation at the frigid temperatures appropriate for their orbital distances. Finding such worlds requires technology capable of separating faint planetary light from overwhelming stellar glare. The brightness ratio between a Sun-like star and a Saturn-mass planet exceeds 10,000 to 1. Detecting that planet means finding a signal 10,000 times fainter than the blinding background behind it. Here is where the physics becomes especially unforgiving. Young planets glow brightly from residual formation heat that has not yet radiated into space. These hot worlds emit strongly at near-infrared wavelengths accessible to many telescopes. But older planets that formed billions of years ago have cooled considerably. Their thermal emissions peak at longer mid-infrared wavelengths that only specialized instruments can detect. Alpha Centauri A's age works against every traditional detection strategy. The planet's astronomers hoped to find there would be cold, dim, and buried behind one of the brightest objects in the night sky. Then there is the motion problem. Alpha Centauri possesses one of the largest proper motions of any naked-eye star in the sky, racing across the celestial sphere at approximately 3.7 arcseconds per year, an angular distance visible to the unaided eye over human lifetimes. This motion sounds small in absolute terms, but represents significant displacement during the precise observations that any serious planet-hunting telescope requires. The star must be continuously tracked to sub-arc-second accuracy just to keep it centered behind a coronagraphic mask. Errors of even 10 milliseconds degrade instrument performance and allow stellar light to leak around mask edges, flooding the detector with exactly the contamination astronomers are trying to eliminate. Finally, the galactic background creates identification chaos that plagues every observation. Alpha Centauri lies directly in the plane of the Milky Way, where thousands of faint background stars crowd every field of view. Any detected signal must be carefully distinguished from these unrelated sources. A faint point of light could be a planet orbiting Alpha Centauri A, or a distant galaxy billions of light-years away, that happens to align with the nearby stellar system during a particular observing window. Separating genuine planetary signals from this crowded cosmic wallpaper demands a level of rigor that goes far beyond what most exoplanet surveys require. So, the system that should have been the easiest target in the sky became the hardest. Too bright for standard detectors, too close for clean coronagraph suppression, too fast for standard tracking, too contaminated by its companion, too old for its planets to glow conveniently on their own. For generations, every attempt to peer into this system came back empty. And that is exactly why what happened next was so extraordinary. The James Webb Space Telescope was never designed for this. Engineers built JWST to study the most distant galaxies in the observable universe. Objects so far away they appear as faint smudges, even through the most powerful instruments ever constructed. Its detectors were optimized for capturing ancient photons that traveled billions of years across cosmic space before reaching those golden mirrors orbiting 1,000,000 miles from Earth. Pointing this exquisitely sensitive instrument at one of the brightest objects in the night sky seems counterintuitive at best, like using a submarine to climb a mountain, like wielding a scalpel to fell a redwood. The technical challenges appeared insurmountable to many astronomers who initially dismissed the entire concept as impractical wishful thinking. The telescope cost approximately $10 billion and took more than 20 years to design, build, test, and deploy. Nobody wanted to risk damaging priceless detectors by pointing them at stellar furnaces bright enough to cause permanent harm. The conservative approach suggested avoiding bright targets entirely and focusing on the distant universe JWST was built to explore. But astronomer Charles Beichmann refused to accept conservative approaches. This veteran researcher from NASA's Jet Propulsion Laboratory had dreamed of detecting planets around Alpha Centauri since before JWST even launched. He assembled a team willing to attempt what others considered impossible. His proposal used JWST's mid-infrared instrument called MIRI to search for thermal emissions from potential planets around Alpha Centauri A. The concept relied on detecting heat rather than reflected starlight. Planets absorb radiation from their host stars and emit this energy as infrared warmth. A world orbiting in the habitable zone of Alpha Centauri A would reach temperatures between 200 and 350 Kelvin, cool enough to emit mid-infrared radiation at wavelengths where MIRI achieves peak sensitivity. The physics strongly favored this approach for a mature planetary system like Alpha Centauri, where any planets would have long since cooled beyond what near-infrared instruments could detect. MIRI includes a coronagraph designed for exactly this purpose. This specialized instrument places a physical mask over the star's position on the detector, creating an artificial eclipse that suppresses stellar light while allowing fainter objects at slightly different positions to remain visible. The coronagraph works through destructive interference. Light waves from the blocked star combine in ways that cancel each other out, reducing brightness by factors of hundreds or thousands. Meanwhile, light from objects positioned slightly away from the mask center passes through relatively unaffected. The contrast between suppressed stellar light and preserved planetary light is what makes detection possible in the first place. For most stellar targets observed by JWST, the coronagraph performs beautifully. Stars at typical exoplanet hunting distances present manageable brightness levels that fall well within instrument specifications. Standard target acquisition procedures lock onto these stars without difficulty. Observations proceed according to established protocols refined through hundreds of successful campaigns. Alpha Centauri shattered every assumption underlying those standard procedures. The system presented unique complications that threatened to ruin any observation attempt before it could even begin. First, and most fundamentally, the star moves. Alpha Centauri's enormous proper motion means the telescope must continuously adjust its pointing to keep the star centered precisely behind the coronagraphic mask. Errors of even 10 milliseconds degrade coronagraph performance and allow stellar light to flood the detector. Second, the binary companion creates observational chaos that no single coronagraph can solve. Alpha Centauri b orbits close enough that its brilliant light scatters contamination across the entire field of view, and no instrument in existence can simultaneously block two bright stars at different locations. Third, Alpha Centauri A is simply too bright for standard JWST operations. The telescope's fine guidance sensors were not designed to lock onto objects this luminous. Brightness limits existed specifically to prevent detector damage from exactly this type of observation. The solution that emerged from months of careful planning was a technique called blind offsetting. Instead of pointing at Alpha Centauri A directly, which would overwhelm the guidance systems, the telescope would first acquire a nearby reference star of manageable brightness called Epsilon Muscae, a red giant located approximately 330 light-years away. From that anchor point, the telescope would perform a precisely calculated offset to position Alpha Centauri A behind the coronagraphic mask without ever looking at it directly. This blind maneuver required knowing the exact positions of both stars to accuracies measured in milliseconds. The calculations incorporated Alpha Centauri's rapid proper motion and its significant parallax. At a distance of only 1.34 parsecs, the star's apparent position shifts by 750 milliseconds as Earth orbits the Sun. This parallax motion creates seasonal variations that must be precisely accounted for when calculating offset coordinates. Every observation required fresh calculations based on the exact date and time of execution. Coordinates valid in January would place the star in the wrong position by March. The team developed software pipelines that automatically computed updated offset values based on observation scheduling. Nothing could be assumed constant when targeting a star that moves measurably against the celestial background every few weeks. The first observation attempts occurred in 2023. They failed completely. Technical difficulties rendered the data entirely unusable. The telescope struggled to maintain precise positioning while simultaneously compensating for target motion and extreme brightness. Coronagraph performance degraded below levels required for planet detection. The contamination from Alpha Centauri B scattered everywhere. Initial failure would have discouraged many research teams. The difficulties seemed to confirm what skeptics had predicted from the beginning, that Alpha Centauri was simply too challenging for JWST to observe productively. But Bachmann's team refused to abandon their goal. They regrouped, analyzed every failure mode, rebuilt their approach from scratch, and prepared for another attempt. In mid-2024, the team implemented their refined approach. Test observations demonstrated that the modifications worked. JWST could finally observe the impossible target with sensitivity approaching theoretical limits. The team requested and received approval for a full observation campaign. In August 2024, the telescope executed 3 long observation sequences pointed at Alpha Centauri A. Each exposure lasted hours as the coronagraph blocked stellar light while detectors collected whatever faint signals emerged from surrounding space. The team watched data stream back from 1,000,000 miles away with a mixture of anticipation and anxiety that had been building for years. The raw images showed exactly what astronomers expected from such a challenging observation: a chaotic mess of light contamination, diffraction patterns, and detector artifacts covering every frame. Alpha Centauri B blazed near the top of each image, its scattered light creating bright streaks and halos extending across the entire field of view. The coronagraph produced complex ripple patterns as stellar light bent around mask edges through diffraction. No human eye could identify anything meaningful in these raw data products. The images appeared as abstract noise patterns with no obvious astronomical information content. Extracting useful science required sophisticated processing techniques developed specifically for high-contrast coronagraphic observations. The team employed a method called reference star differential imaging. They observed other stars using identical coronagraphic configurations to create templates showing how the instrument behaves when no planet exists in the field. Subtracting these reference templates from the Alpha Centauri data removed systematic patterns arising from optical effects while preserving genuine astronomical signals that appeared only around the target star. Additional algorithms, called principal component analysis, stripped away remaining contamination sources by identifying and removing correlated noise patterns that reference subtraction alone could not eliminate. Layer by layer, component by component, the data reduction process began revealing what lay hidden beneath the stellar glare. What emerged from this painstaking analysis shocked everyone involved. At a separation of approximately 1.5 arcseconds from Alpha Centauri A, a faint point of light appeared in the fully processed images. This object, designated S1 by the Discovery team, shone more than 10,000 times fainter than its brilliant host star. Its angular position placed it roughly 2 astronomical units from Alpha Centauri A, comparable to the orbital distance of Mars in our own solar system. The detection achieved statistical significance of 5.5 sigma, meaning the probability of that signal arising from random noise rather than a genuine astronomical source drops below 1 in 10 million. Something real had been detected beside our nearest sun-like stellar neighbor. The room where scientists watched those processed images materialize on their screens went very quiet. Then someone said the words that everyone was thinking. Is that a planet? And nobody, not a single person in that room, had a confident answer. Rigorous testing followed immediately. The team needed to eliminate every possible alternative explanation before claiming a planetary discovery. Extraordinary claims require extraordinary evidence, and a planet around Alpha Centauri would rank among the most significant discoveries in exoplanet history. Could S1 be a distant background galaxy masquerading as a nearby planet? The team cross-referenced the detection position against every astronomical catalog containing known background sources. Nothing matched. No previously identified object occupied that location. Could S1 be a foreground asteroid passing through the field during observations? Motion analysis examined whether the detected signal shifted position during the observation period. It remained stationary relative to Alpha Centauri A, ruling out nearby moving objects entirely. Could S1 be an instrumental artifact created by complex optical interactions within the coronagraph? The team performed exhaustive injection recovery tests, inserting simulated planetary signals into raw data and verifying they could distinguish genuine detections from processing artifacts. Real signals behave differently than artifacts in subtle but measurable ways. S1 passed every test designed to expose false positives. The team also split the August observations into independent portions and analyzed each separately. Both halves reproduced the S1 signal at consistent positions and brightnesses. Genuine noise fluctuations rarely behave so consistently across independent data samples. Then came a detail that sharpened the excitement considerably. In 2019, astronomers using the European Southern Observatory's Very Large Telescope in Chile had captured a faint signal near Alpha Centauri A, designated C1, appearing at approximately 1.1 astronomical units from the host star. That ground-based detection never achieved confirmation status. Earth's turbulent atmosphere constantly distorts incoming light, and adaptive optics systems can only partially correct these distortions. The signal appeared marginally in processed images, but could not be definitively distinguished from residual atmospheric artifacts. Most astronomers filed it away as an interesting hint requiring better data. But now, 5 years later, JWST had detected something in nearly the same region. 2 completely different instruments, 2 different observatories, 2 different detection techniques, both pointing at the same neighborhood around our nearest sun-like star. What if C1 and S1 represented the same object observed at different orbital phases? A planet on an eccentric orbit would appear at different distances from its host star depending on when observations occurred. The 2019 ground detection and the 2024 space detection might both be capturing brief glimpses of a single world moving along an elongated path. If this hypothesis held, combining both detections would dramatically constrain possible orbits. A planet must follow a path that places it at approximately 1.1 astronomical units during 2019 observations and approximately 2 astronomical units during August 2024. The idea transformed two uncertain hints into a coherent narrative and made the case for a genuine planet considerably harder to dismiss. The preliminary analysis painted a striking physical picture of what S1 might be. Its effective temperature sat around 225 Kelvin, roughly negative 48 degrees Celsius. Mass estimates based on brightness and temperature suggested somewhere between 90 and 150 Earth masses, placing it firmly in Saturn's weight class. Saturn itself tips the scales at approximately 95 Earth masses. This was not a scorching hot Jupiter blasting thermal radiation from a tight orbit around its star. This was a cold, mature gas giant sitting in the outer reaches of the habitable zone, the circumstellar region where rocky planets could theoretically maintain liquid water on their surfaces. The object that appeared in those processed images was not just a planet candidate. It was potentially the most scientifically valuable directly imaged world ever detected. And confirmation was now the only thing standing between a tantalizing signal and a discovery that would reshape planetary science entirely. The Space Telescope Science Institute granted directors discretionary time for urgent follow-up observations. This precious resource provides rapid response capability for scientifically critical targets that cannot wait for normal proposal cycles. The Alpha Centauri planet candidate qualified without question. 2 additional observation campaigns were scheduled, one in February and one in April 2025. If S1 represented a genuine planet, it should appear at different positions consistent with orbital motion between the observing epochs. The amount and direction of movement would constrain the orbital period and geometry. The scientific community held its collective breath. Rumors circulated through astronomical conferences and online forums. The closest sun-like star to Earth might actually host a directly imaged planet, a cosmic neighbor that philosophers and scientists had wondered about for centuries might finally reveal its planetary family. The implications extended far beyond simple detection statistics. Alpha Centauri. A resembles our Sun in nearly every measurable way. Same spectral class, same surface temperature, same age, same invitation to life. Finding a planet around this genuine solar twin would provide unprecedented opportunities for comparative planetary science that no other directly imaged system could offer. The February 2025 observations proceeded flawlessly from a technical standpoint. Every system aboard JWST performed exactly as designed. The complex blind offset maneuver placed Alpha Centauri A precisely behind the coronagraphic mask. Detectors collected photons for hours while the telescope maintained rock-steady pointing. Data streamed back to Earth at the speed of light. Eager scientists waited at their terminals, ready to process images that might confirm the most significant planetary discovery in decades. The same analysis pipeline that had unveiled S1 6 months earlier ground through the February data with mechanical precision.